So when we ended the period yesterday, we were looking at the complement of an event. And we said the complement of event A is simply not A. Or we could also notate a complement by saying a complement, but the way I'll use it today is the apostrophe. I don't really use the C, I tend to use the apostrophe. So that apostrophe means a complement. And then we can even draw a Venn diagram where a complement is everything outside of A. So our event A is the circle. A complements everything outside the circle, but inside the rectangle. What's the rectangle represent? Sample space. Good. Rectangle represents your sample space. So let's do an example with this. Let's suppose we roll a six-sided die. The event that the die would land on an even number would be 2, 4, and 6. What would the event be that the die does not land on an even number? 1, 3, and 5. Good. Now, if this is E, I could call this E complement. Remember that apostrophe means complement or not E. Or you could also, as they did down here, use a C for complement. You need to be comfortable with either way. So the superscript C stands for complement. Now, if I combine E and E complement, then that probability would equal 1, meaning it's guaranteed, I guarantee it, that you'll get 1, 2, 3, 4, 5, or 6 if you roll a die. Now, we can even take this a step further and draw a Venn diagram. So if we let the rectangle be the sample space, like we said earlier, then I would need to draw a circle to represent E. And the shaded area is the event not E. Well, if y'all are like me and you don't want to waste a ton of ink or pencil lead or highlighter or whatever you're using, you don't have to shade this. I would just label it. So inside here we have E, outside we have E complement. Now, what numbers are in E? 2, 4, 6. 2, 4, and 6. What numbers are in E complement? 1, 1, 3, and 5. Notice I just kind of scatter them all around. The 1 doesn't have to be where I put it, as long as it's in the box, but not the circle, you're good. Just scatter them around out there. Or you can even be one of those where it's like, ooh, here's my circle. 2, 4, 6. 1, 3, 5. However you want to do it. I mean, I don't really care. You don't even have to draw this Venn diagram. These are your notes. That's our Venn diagram for this problem. If you're good on that problem, let's turn the page. That way I'll know. I'll see everyone turning the page, then I'll know that y'all are ready to move on to the next topic. Now, anybody writing, so that means we must be good. Okay. Where's my notes? Okay, the next thing we're going to look at is the union of A or B. So that consists of all outcomes that are in at least one of the two events. That means they could either be in A, they could be in B, or they could even be in both. We note the union using this U-looking symbol. Technically, this is called a cup. That's what the technical name for that symbol is. But we read it as union. So A union B. So the one way to think of a union is consider a marriage or union of two people. When two people get married, what do they do with their possessions? They share them, right? They put them together. So the bride takes all of her stuff, the groom takes all of his stuff, and they put it together. And then they run away and live happily ever after. There's also another version of that. According to my dad, since I'm not married, I just get my wisdom from him. He's like, really, what happens? You don't put them together. Really, you get married, and how the wife sees it is what's hers is hers, and what's yours is now hers also. So, might as well just give it all to her, because it's all hers. Anyways, similar concept with the unions. All of A and all of B are put together. So suppose a six-sided die is rolled. The event that the die would land on an even number would be 2, 4, and 6. We're going to call that event E. Event P is that the die lands on a prime number. So 1, 2, 3, and 5. What would be the event of E or P happening? So if we said E or P, what would that look like? What numbers would be in that? 2, 3, 4, 5, and 6. Why didn't we list the 2 twice? You only need it once. It's the same thing. It's kind of like if you get married and you're already living together before you get married, which evidently is the thing now. You're not going to get married and then boom, as soon as you get married, you automatically have 2 apartments. And it doesn't work like that. So you just need it once. This is an example of the union of 2 events. Now let's look at a Venn diagram for unions. If A and B are our 2 events, we could represent the union by drawing a circle for A and a circle for B, and everything inside those circles is included in the union. Now, in this, just drawing the Venn diagram for a union, do they have to be overlapping? No, they don't have to, unless they have something in common. Then they do. But it's possible to do a union where you have nothing in common. This is A union B, A or B. Let's draw a Venn diagram for our dice example. So we have E or P occurring. One way we could represent this is a Venn diagram. Go back. Let's draw our own diagram. So draw your rectangle. And then what 2 events did we have? What were the letters for those? E and P. Did they have anything in common?
Yes.
A 2, so we do need these to overlap. What should go in both circles, like on the intersection here? A 2. If I let this left one be E, what other 2 numbers should go in here for E? 4 and 6. The right circle is P. What other 2 numbers should go in here? 3 and 5. Now I'm rolling a die. So what number needs to go outside the union? 1. Why is 1 outside? It wasn't in the cluster, it's not even, and it's not prime. So it gets stuck all on, because 1 is the loneliest number. I'm pretty sure I just totally missed the tune, but I know that is part of a song. Okay, so they're drawing their Venn diagram. We talked about that. E or P would be anything inside the circles. We talked about that. Let's look at, so that was union, where it's just what's in the circles. Now let's talk about intersections. So let me ask you this. If you were to go, like, exit the loop, like you're coming to the school from Ford Chapel, down there by the Loves and the Chevron, if you were to stand in that intersection, how many roads would you be on in that instant? 2, right? Same concept with this one. If you have the intersection of 2 events, that means it's what is in both of the events. They have, whatever unit you have must be in both. So this symbol, it's the upside down U shape. It's technically called a cap. A cap. Yep. Like, why are you capping? A cap. That's what it's like when you type this in Microsoft Office using the math language. You would do a slash and then type the word cap, and then when you hit space, it'll appear. I only know that because I did some math graduate classes, and I had to type all the equations. It actually isn't that bad once you learn it. Once you learn how to type it, it goes pretty quick. Okay, anyways. The intersection of A and B consists of all outcomes that are in both of the events. So it's that part where the circles overlap each other. That's the intersection of A and B. So let's go back to our dice example. What would be the event that E and P both happen at the same time? A 2, right? So we could say that E intersect P is equal to the event 2, the simple event 2. Let's use that vocab. The simple event 2. They use the word and, but I want us to get used to using the symbols. Let's get used to using the symbols. Now, we can also draw this intersection as a Venn diagram. So, if we did the Venn diagram, it would look similar. Let's draw the Venn diagram just like we did for the union. We've got our E here. We got the P. 2, 4, 6. What were our other two numbers? 2 for prime. 3 and 5. And then outside we had a 1. So the intersection of E and P would be this area right here. There's our intersection. So it's where the two circles overlap. Now, right now, you may be thinking, okay, Venn diagram's great, whatever. I mean, they're not really helping me visualize this much. But you can also use these when we get to talking about probability and get to some of the more complicated probability type problems. You can always break them down into Venn diagrams, and then that'll help you kind of understand what's going on. Just to kind of get a survey, how many of y'all tend to be more visual? It helps you to visualize a problem rather than writing stuff down. Okay, so when we get to those kinds of problems, I'll show you how to do it just writing the facts down, But then we'll also incorporate Venn diagrams, so that way you can visualize what's going on. Okay, so then we have, oh, wait a minute, no, okay. Yeah, so here it's just saying E and P would be only the middle part. So we've already said that. Mutually exclusive or disjoint events, or events that have nothing in common. For instance, can a number be both even and odd at the same time? No, it can't be. Zero, I heard someone say, what about zero? Well, zero is actually up for debate. It's a huge debate among mathematicians. Is zero even? Is it odd? Most mathematicians say zero is even. Some say it's odd. It's not. It really depends on the book you're looking at, honestly. But for the most, zero aside, you can't be both even and odd at the same time. So those would be an example of disjoint events. They're separate. They cannot occur. Another example would be flipping a coin. Can you land on both heads and tails at the same time? No, it's got to be one or the other. So those are mutually exclusive events. So let's suppose we roll a die. Consider the two events, A being 2, B being 6. On a single roll, is it possible for A and B to happen at the same time? No. You can't roll a 2 and a 6 at the same time if you just have one die. So let's write that because I think that's a question on your notes. Let's answer that with a big no. Can't happen. These are mutually exclusive events. So if we were to draw a Venn diagram for them, the circles would be totally separated from each other. This would be A, this would be B. A gets a 2, B gets a 6, and then we just sprinkle the rest around the outside of them. 1, 3, 4, let's see, 5. Just sprinkle them around the outside. You don't have to put them where I put them. If they're outside the circle, they're good. Yes. Yes, you do. So notice here, let me back up. Notice that the intersection here is empty. Just a little bit of extra math terminology. If we were to do the intersection of A and B, is there anything that these two sets have in common? No. So we would say this is the empty set. This symbol here That symbol means empty set. Or, in other words, nothing is in there. This is the empty set. They have nothing in common. Okay, let's talk about mutually exclusive for more than two events. So let A1, A2 to AK denote K events. So we've got K different events happening. If I wanted to say or, so A1 or A2 or A3 or all the way to AK, in order to be included in that, all we need is to appear in one event. Then we would be in a union of all of them. However, if I did the intersection of all K events, then they're only mutually exclusive if it appears in none of these. So it can't even be in A2 and AK together. To be mutually exclusive, all events have to be separate. Be like if you bought a die, and for whatever reason, somehow you could roll a 2 and a 4 at the same time. It's like, I think your die is defective. Can I get my money back? You wouldn't want to be able to roll 2 numbers with one die. So let's get some practice with Venn diagrams. On the following slides, we're going to have students that are enrolled in statistics, which will represent with an S, calculus, which will represent with a C, and computer science, which will represent with a CS. We want to indicate what relationships the shaded regions represent. And we have to use our terms that we learned today: complement, intersection, and union. So let's look at this first one. What's going on here? What's this showing? What 2 circles are fully shaded? Calculus and computer science. But can I say calculus and computer science, or do I have to say calculus or computer science? And? Remember, and means talking about the intersection. Is only the intersection shaded? No, so I have to say calculus or computer science. So I'm going to write it in. I'm going to write comp sci instead of computer science. That's how we would put it in words. If I wanted to use symbols, what would I say? C and then CS, what symbol would go here in the middle? The U. If it's or, you're going to put the cup or the U. You can tell I'm an Aggie because anytime I see CS, I automatically think College Station. Anytime I see CS.
Wait, so and is what?
What's that? And means they have to be in, like in this case, they would have to be in both calculus and computer science. If we said that this represents calculus and computer science, they would have to be in both. The only group that's in both is right here. This person, if they're out here, they're only in computer science. So we couldn't say and because they're only in one of them. Does that make sense? So or means they could be in either or both. And means they have to be in both. Okay, next one. What's going on here? Statistics and computer science?
Oh, that one? Oh, no.
It would be, yes. Statistics or computer science? Oh, I see. Y'all went down. I went over. Okay. Yeah. Statistics or computer science? Yes, you may. Okay, now I have to be careful here though, because if I said statistics or computer science, I'm including this area. But does my, other than me just coloring it in now, does it include that area? No, so how can I cut that out? What do I have to say? So I'm in statistics or computer science, but not calculus. Let's put that. But not calculus. Now, do I know the symbol for the word but? No. What do we say? And not calculus. Now, I'm going to have to put the first two in parentheses because I want to say everything statistics, everything computer science, and then do like we just did, go through at the end and say not calculus. Let's put this in the symbols. I want to have S or computer science. What's the symbol for the and? Okay. And then how do I say not calculus? Well, that means empty set, so it wouldn't be the 0 with the line. Go back. It's what we talked about at the very beginning today. That's right. It'd be an apostrophe because the apostrophe is the complement of calculus. So what we want to remember here is PEMDAS, as far as putting the parentheses in there. Even though this is more logic at this point, PEMDAS applies. We start with the parentheses first, And then we're going to cut out the calculus of what's left. So statistics are computer science and not calculus. Questions on this one? Next one. What's going on here? That's right. You nailed it perfect. Statistics. Statistics and computer science. And not calculus. You can put these in parentheses if you want to. In this case, you don't have to do parentheses, but you can. Let's put this in symbols. We have statistics and computer science and not calculus. Again, you don't have to put parentheses around these first two, but you can. Because they're the same symbols, that's right. If they're all the same symbols, you don't have to worry about parentheses. Anyone still trying to write anything down from this slide? Okay, next one. Last one for this topic. What's happening here? Statistics. And what were y'all saying? And not computer science. I heard that. And what else? And not calculus. Now, this is one way to write it. This is one way you could write this. There's actually a shorter way. So you could say it this way, or you could say statistics and not. Take both and nots out. Computer science or calculus. Instead of saying statistics and not computer science and not calculus, just say the and not once and then combine the ors. Combine the two. So let's put this in symbols. Statistics and not computer science or calculus. Questions on this example? Okay, so let's get out that half sheet that I gave y'all. If you already put it away, I'm sorry. Let's get it back out. And like I said, AP, if y'all want the half sheet, I have, I guess, one extra up here. You're welcome to it. Okay, so the reason I gave y'all the half sheet dual credit is because on your assignment, there's some problems that it's like we cover everything in these first two sections, or really the first three sections of this homework, but this one topic. So I wanted to give y'all this one topic. That way you could do most of the homework. You can actually do all of the homework. No, not quite. We need a little bit of 6.3. But this homework, again, is not due till Monday, so that's okay. We have time to get to it. The fundamental counting principle says that if one event can occur M ways, and a second event can occur in N ways, then the number of ways that both events can occur in total is M times N. Now, if you've had geometry, you may recognize a problem that we're about to do for this next example. So if you want to pick an outfit to wear out of 6 shirts, 3 pairs of pants, and 4 pairs of shoes, how many different outfits could you pick? Well, let's write down what we know. How many shirts do we have? 6. So I'm going to pretend that this isn't here, even though I know y'all have the answer there, but let's pretend it's not there. So we've got 6 shirts. How many pairs of pants do we have? 3. I'm just going to say 3 pants. How many pairs of shoes? 4 pairs of shoes. I'm going to just say 4 shoes. So the total number of outfits that we can make would be 6 times 3 times 4, which gives us 72. That's right. There's 72 outfits that you could wear. That's all the fundamental counting principle says. Now, we can take this a step further and go just a little bit deeper, where we have to think a little bit more. I can't keep it that easy on you. I need to erase this because I wrote all over this next problem. Okay, so let's say the school district is assigning ID numbers to students. They have a rule that says the first digit cannot be a 4 or a 5. The last digit must be a multiple of 3. How many 5-digit numbers can they assign? Well, what are our counting numbers? 1 through 9, right? But what digit can we also use if we're making a number? 0, right? So I'm going to write those here. 0. I'm not going to write all 9, so I'm just going to put dot 9. So these are all the options we can pick from for each digit. Do y'all agree? If I'm giving someone an ID number? So what I recommend on these, if you're making numbers, figure out how many digits you can have. In our case, how many digits? 5. So make 5 blanks. 1, 2, 3, 4, 5. Now you can go back and see what conditions it gets. So it says for our first digit, that one right there, we cannot be a 4 or a 5. So how many options am I left with? If I can't be a 4 or a 5, how many options does that leave me with from our list here? 8. Okay. The other condition, the last digit must be a multiple of 3. Okay, well, again, think back to our options that we can pick from. What are our multiples of 3? 3, and then 6, and then 9. How many options does that give me then? 3. So I only have 3 options for the last digit. Does it give me any more conditions? No. So that means I am free to pick whatever digit I want for the rest. So how many options do I have for the second digit? The third digit? The fourth digit? So to figure out how many total ID numbers, you just multiply all the way across, and that gets you 24,000 ID numbers. So, like I said, all the fundamental counting principle does is tell you that if you break each happening, if you will, into its own event, you can multiply the ways each event can happen and get the total number of possibilities. That's what it's saying. Questions on that? Okay. Like I said, there's a few problems on this assignment that I gave y'all today that deal with that. So, okay, that's it for section 6.1.